For the next 30, 35 minutes, I'll take you across the ocean, Switzerland, where we work the general energy division of Scherrer Institute. And for those that do not know the Swiss system, we belong to the ETH domain, and our job is to construct and operate these large research facilities. So amongst others, we have neutron installations, an X-ray field laser, and synchrotron instruments. So our group operates one beamline, the super XAS beamline, synchrotron, and will start commissioning the second beamline combines X-ray absorption spectroscopy, outer diffraction, and total scattering. These kind of. So the title of my talk is really not just putting buzzwords together. We really need this. Doing operando, transient, X-ray absorption spectroscopy, really get inside Catalytic. And so to this audience, I probably do not need to introduce the operando approach, but just very briefly, you take a catalyst, in this case it's a ornate metal catalyst, you put it in a reactor, blood flow reactor, you pass your gases over it, you look at activity or selectivity, use mass C, they simultaneously use the strength hard X-rays that they can penetrate through your reactor bed, and you get information either on the structure, the electrons. Okay, so we are after the structure, activity, or structure selectivity relationships, and these, as I will show during the remainder of the talk, really help to optimize or design new catalysts or catalysts. Two technical slides. One says this is a super XAS beamline. We have beamline for operando X-ray spectroscopy, where we focus on one hand side to have all the infrastructure available, like reactive gases, potential staff. And the other side continuously optimize our methods to be very sensitive catalytic reactors. We have a probe setup where we can populate different wavelengths, the laser to do laser bound X-ray probe spectroscopy on photocatalytic systems, focusing on the relevant time scales from nanoseconds to microseconds. We continuously develop these X-ray emission-based spectrometer to do high emission results. The rest is detected slugs, for example, but also to do X-ray emission spectroscopy, looking, for example, at various support positions. And then lastly, we really optimize time resolution that we can get X-ray absorption spectroscopy by pushing this technique called quick access. And here we really optimize all components of the. So you need to have a fast scanning monochromator to scan through your energy. You need a very fast detector. Here we profited from the development of the Vlaam group at the University of Wuppertal to have the graded ionization check. We introduced a split detector to be able to measure XAS spectra fluorescence mode, so when you have a lower concentrated metal interest. You have then a data acquisition system where you sample at very high rates, so you basically oversample your data, which you can then use to filter out noise, right? So you can cut out. So here you see spectrum collected a few tenths of milliseconds. And if you use this filtering of noise, you end up with quite good excess spectrum, quite a long range. Obviously, you need software for on-the-fly treatment of your data, so you can really look at your time data. And finally, if you collect data for a few hours, you end up at 10,000 spectrum. So you really need to work new data mining. Okay, so I'm in this fortunate position to have a very great team, and we are a bit different compared to a professorship in that we have several senior scientists. We were very lucky to meet them recently, each of which have their own research to some extent. I will show work today on selective catalytic reduction, which is partially done by Adam. I will show some work from Olga at dehydrogenation ethanol, And I will show some examples. One of them is Anna from Scherrer. You see in the audience, of course, nesting, rock oxidation. Dominique is also in the audience, per year. These are our funders and the pieces. This is an outline for the remainder. So what I want to show is you really need to look at the system in all angles. Okay, so the first example where we look at oxygen evolution over a perovskite material, there you do form your active site actually only under operating conditions. Okay, so you only form under OER. The second example, we look at the mechanism of selective catalytic reduction of nitrous oxides. Okay? And in order to understand this whole catalytic mechanism, you need to have a transient. The third example, we look at the production of aldehyde, oxidative dehydration, ethanol, and here I show that you can actually measure rates of structural change here, these kind of reagents. The last example, heterogeneous oxidation. So here we look at reaction coordinates. We do simple kind of transient experiments to get inside the mechanism, but also the active side. Heterogeneous one. Okay, so that's the first example. And this is really a longer journey that we took together with our electrocatalytic collaborators. So we have Claudia from Smith, right? This research to new materials for OER reactions. Okay, so if you want to produce green hydrogen, one way to get it is to use these electrolyzers, where you evolve hydrogen cathode side, you evolve oxygen on the anode side. And it's for the oxygen evolution reaction, which is four-step process, that you need to add a lot of energy, right? So you need a high overprotection. And this is mainly due to the sluggish reaction dynamics. So if you want to optimize production of hydrogen, you should really focus on the oxygen evolution reaction. And you should focus on replacing iridium. So iridium oxide is state-of-the-art both in terms of stability as well as activity. The scaling up of these kind of electrolyzers using iridium oxide is not possible. So one of the materials that evolved over the years are these perovskites that can be used as potential OER catalysts in alkaline. These are fantastic structures. They are very flexible. You have the A side here in the middle of this perovskite, E sides where you have octahedra that are corner. And the possibility of changing and putting in different elements is very good. So we are looking for the scriptors to find the highest potential activity of these perovskite materials. And there was this nice study by the group Scherrer back in 2011, where she showed that if you have a certain filling level, your 3D transition levels, easy levels, you'll reach the highest activity. So in this case, with this very strong causing happens. Okay, so they came up with the design principle for the OER reaction based on looking at the bulk properties of the as prepared materials and comparing them to the OER activity. So we got interested in these materials a few years later. When all these papers appeared that when you add some carbon to the system, your material obviously becomes a lot more active. Okay. So these experiments also been repeated by us. So in blue, you have a typical BSDF material. Then you add carbon, and carbon is a bit more, right? So you do some chemistry. Then you end up with a material where the concept of oxygen evolution gives a lower over potentials. And so you have a more. And the question that we have is this really an effect of just enhanced layer conductivity or is something else? predicting sources spectroscopy, formula X-rays, absorption, even out. And basically what we see is that our cobalt atom, where cobalt is reduced cobalt 3 plus to cobalt 2 plus. Right? And this fits perfectly in this volcano type model before. So this really makes it very yeah. Now, adding carbon to the system is not something that you can really do on large scales, that you solidification, solvent. So we look for another way of producing this ESEF, cobalt reduced state. And for that, we went to our colleagues at EMPA, another institute in Switzerland, where they have this flame spray synthesis. So we produce also very small particles, 5 to 7 nanometers in size. So called their nano ESEF particles. And if you compare their activities on here, the current over potential, you see that this material is even more active as the state of the uranium process. If you can measure the cell spectrum, now you're really all experts. You see that we were quite successful. So we really produced ESEF with cobalt 2. That's why we should have stopped. We like to go around and moving the titles. We kept on going. We developed on ourselves to do these electroanalytic studies really as close as possible to experiments that you would do in the lab, right? Still RD. So we have a thin electrolyte, we have a thin electrode, we have a flow of the electrolyte, and we can basically run our standard polarization and durability. It's extremely important here to have a thin catalyst. And so that's something that we fortunately had to learn the hard way over the years. On the one hand side, this thin film allows you to completely wet your electrode. And the other side, as soon as you start to evolve gases, oxygen in this case, these bubbles can lead to delamination, necroactivity, completely changing your results. So let's look at our ESEF material under OER conditions. So here we have an anodic scan. Simultaneously we collect stuff. So below the onset oxygen evolution, see absolutely no change suspect. And as you can expect, as soon as we move into the onset of oxygen evolution reaction, we see that cobalt slowly starts to oxidize. And if we really evolve oxygen, cobalt is oxidized back to treatment. So there goes our design principle. Right? So we were convinced, we knew what was going on, we need cobalt plus. If you look at this material, while it's active, cobalt treatment. And it's summarized here. Again, the anodic scan together with the shift in position of action position. And basically what we learned is you really need to study conditions. So what is going on? For that, we need to look at the excess part of the spectra. So here you see the Fourier transformed excess spectra. We focus now only on the second peak. So we start with our black line, right? So these are our spectra collected before the onset of oxygen evolution. And this peak is at a distance that is characteristic of quarter sharing of the heat. So if you remember this picture of this perovskite, so at that distance you have cobalt iron, this quarter. So when we move into the OER region, we go from the black line towards the red line, and what you see here in the dotted line are variations or difference. Basically, what you see is that the second contribution is coming up at lower bond distances. So characteristic bond distances of phase and edge of the heat. And these you find in cobalt iron oxyhydrous. Okay, so what we see is that our active phase is formed under OER conditions, and this is basically a cobalt iron oxyhydrous. So this is basically our proposed mechanism, since we proposed it many other studies came out to show basically the same thing. So our perovskite is more or less a precursor for our activity. So under conditions where we involve oxygen, we also have this lattice oxygen evolution, which leads to a partial dissolution of your elements. And due to surface-induced precipitation, you form this very highly dynamic cobalt ion oxyhydroxide. This is relevant. So we send our samples to a proton site. They have these technical alkaline membrane electrolyzers, and they compare them towards their state-of-the-art videos. So at low overpotentials, our DSCF material is even a bit more active. And if we look more importantly, I would say, so if we look at the stability of this material, we compare it to iridium oxide. So at least 5 times the brightness of the stability. Next time. So let's switch gears to gas after treatment catalysis. Currently here, I want to show the need to do transient of our. So here we look at the diesel exhaust gas catalyst, but basically for small cars, we do the standard Scherrer reaction, right? So using a selective agent, you selectively reduce nitrous oxide in the presence of carbon monoxide to convert fuel that you want to oxide, reducing nitrogen and water. So the state of so your material needs to be hydrophobic stable. And now with cars getting more and more fuel efficient, these materials need to be active even under quite rich oxygen-rich fuel mixtures. So one of the materials that emerged also commercially are these copper chemicals. The chemicide is a small pore size realized. Performance studies have shown that you have about 1 copper atom zeolite. This is a typical conversion curve of nitrous oxide reduction. So you see that the low temperature is helping you because it's not that bad. Now when you drive a car, your core car catalyst is continuously changing conditions, right? So you have changing conditions of temperature, your gas composition changes all the time. And on top of that, ammonia is fed intermittently to the car catalyst. So to mimic these kind of situations, we basically introduced transient experimentation, which is used for a long time, forcing. And an example that I'm going to show here is runoff ammonia. Then when we run such an experiment, so we have a realistic feed, CRP, some water, we cut off ammonia. The feed, and what you see in the MS catalyst test is that your catalyst is temporarily active. Okay? So you see this dip, this green line, it's nitrous oxide. After we cut off, we see that at low temperatures, we do not see that higher temperatures. And this was initially for us to take counter to it, right? So what we simultaneously collect time results from SAS data, and we go from the black line here to the green line at the end after the cutoff model. So for those of you familiar with copper cells, start with mostly copper 1 species, and if we wait long enough, the absence of ammonia will your copper oxide. The approach in our field is that you then take reference materials of copper and the coordination that you expect in samples. We measure the sun spectra, and then we do a linear combination. Okay, so in our starting point, copper is mostly solvated, mostly copper 1, right? Solvated by ammonia species. If we wait long enough, copper 1 gets almost completely reduced, and we end up with copper 2 bound to the zeolite structure, as well as copper nitrate. Okay, from this picture already, you can see that copper nitrate, for example, probably do not adhere to the low temperature. Another way to treat this data set is to actually not use reference. So here we use this chemometric method, multivariate curve resolution methods, which basically give you the so-called pure components, right? So the components, the pure spectral components, the species that evolve during your reaction, right? So where your fraction either increases or decreases during the experiment. So it is very powerful to pick out the species, your top species that change. If under all your conditions your copper never changes, we would not have. Okay, so here we compare the 5 pure components that we obtained using with the references. I color-coded it, so all references actually quite well represented the system that we have, except for this green line, which is our proxy for copper 1 zeolite. So we use here copper 2 oxide, and this is clearly not right. And this we see a lot nowadays with these large data sets that we brought these kind of chemicals. So back to our system. Again, the endless traces here, we see this temporarily higher activity of the catalyst after we cut ammonia to feed. If we look now at the individual bits, so this is time, these are the different fractions present. If you cut off ammonia at low temperature, we see that copper 1 sulfated by ammonia temporarily goes down. We see copper 2 sulfated by ammonia goes down. And it just showed us that low temperature in the catalytic cycle, ammonia locks copper 1 hindering its reoxidation. As this is our rate-limiting step at low temperature. This is how all the components nice test stand where they use a large filter monolith to repeat these experiments at realistic gas our space velocities. Again, here this solid line that cuts the ammonia and feed, and the seed is higher, temporarily higher. And you can use this. So in orange, you have the typical feeding with similar amounts of ammonia to the catalyst bed with the corresponding conversion curve. If you now optimize feeding ammonia, a lot less temperatures, you can almost double ammonia. This is something programmers could do. After this, we started studying ion synthesis 5, which is also used a lot for SCR reactions. It's not very active at low temperatures. There have been a lot of studies that suggest that maybe monomer ion species are active. These are difficult to get, almost impossible to synthesize. Dominic was able to synthesize zeolite dominantly monomer ion species and also a terminal structure. We will get it all tomorrow morning at 8 o'clock. So after the conference, please come up early and we will show you the details. Good. The last 2 examples deal with the formation of acetal. The first one, we looked at selective ethanol oxidation over supported vanadium. So the sample that we used here, this is essential for the absorption spectroscopy. There's a very thin layer of titanium dioxide called silicon dioxide, which is decorated with these oxides. And thanks to Israel Labs, we have these samples to start with, and allows us to get inside redox compound. And so this is the reaction of ethanol, the conversion of ethanol to acetaldehyde. And the question we wanted to address is what is active redox compound in this reaction? So the approach taken here is very similar as for the SCR reaction. We have our sample in the cell, we feed it constant with constant ethanol, and then we periodically switch off and oxygen. Using IR, we then measure ethanol conversion from acetaldehyde formation, and simultaneously we measure time result for suspect. We do this at different temperatures. We then use use the same MCR AMS technique to get a pure spectral components. We get components for the vanadium 5 plus black, vanadium 4 plus blue, vanadium 3 plus red. If we then do similar oxygen cutoff experiments, so here we cut off oxygen, so well, right? So we only have ethanol in the feed. You see that vanadium 5 quickly reduces, vanadium 4 is formed, vanadium 3 plus is formed maybe a little bit later. You can navigate the initial rate of change. Okay? So if you fit the initial rate of change and you do that at different temperatures, you can construct these so-called Arrhenius plots. So here we have the rate of change for vanadium 5 plus, production of vanadium 5 plus, formation of 4 plus, and scale this redox complex involved. Catalytics. And you see that there's a difference between the global reaction rate, acetaldehyde, and this redox couple, and this is a factor. It is a 2-electron process. I'm seeing 2 or 3 redox couples produced. So this was the work done by Anna and supervised. The next example, and also my last example, is looking at a heterogeneous block oxidation over palladium COI1. The major production of acetaldehyde at the moment is still going through homogeneous block oxidation, which uses these chlorinated solvents, where the major problem with this process is really explosive, and also you produce chlorinated fiber. So research 30 to 20 years ago focused on trying to make this process heterogeneous, right? To put your catalyst on support that provides acidity, so that you can run this reaction without chlorine. And the most active and also most stable heterogeneous Wagner catalyst produced today is this palladium copper 0Y. At the time, the group of Jacobs at the University of Leuven showed that using the techniques that they had hand at that time, they basically tried to come up with the structure of the catalytic side, so they proposed copper 2, palladium, copper 2 cluster, if you want, and they concluded also on the other test that they probably have a mechanism in place that is not that different, homogeneous particles. And in the study, there was not a lot more literature. Sedation, and the major reason is that this system deactivates really quickly. And so we stepped in later, so this is work done by Eric, collaboration with Rocco. So we stepped in later, use our transient approach to see if we can learn a little bit more about the active side of the certain mechanism and deactivation. And the approach taken here is a bit different. What I've shown before is we determined the different reaction orders with water, oxygen, and here is only the results of oxygen. So at low partial pressures, this is half water reaction. If you go to mid partial pressures of oxygen, we are at 0. So we set up our experiments in such a way that we just switch from high order to low order, the other way around. Okay. Simultaneously, we collect soft spectra, copper chaos, vanadium. We use experiments and use the same approach to get the spectral components. So for vanadium, we basically have palladium 0, palladium 2 plus. And for copper, we also have copper 1 plus 0, and we find 2 copper 2 plus. Now, if we switch from high partial pressures, low partial pressures, we see that there's a very slow change in the we see this quick change to copper. This copper gets reduced to copper just seen that copper is the site. What we know from just analytic studies is that palladium is the site where ethylene is active. What we also see is that if we wait long enough, copper 1 gets really oxidized partially copper 2 plus. And taking some of the oxygen from palladium, leading to the formation of more palladium 0, and excess and shows that we form 0 pluses. Okay, so this is the major deactivation. So just a summary, so basically what we learned from these studies, more of this is published already. So we learned that oxidation of ethylene plus aldehyde palladium, reactivation of palladium happens. The completion of this palladium cycle happens by copper 2 plus, copper 1 plus, redox couple, oxygen is activated, copper, and we see slow catalytic deactivation due to reduction of 2 plus. Because what I wanted to show is that you really need this operando transient X-ray absorption approach to be inside. So the first example dealt with perovskite catalyst for the oxygen evolution reaction, where we showed that the structure is very dynamic. And so our active sites actually formed under operando. So this marker shows the need to really do studies. The second example, where we looked at ammonia-assisted SCR reaction oxides over copper genocide, showed that the transient experiments really help to get insights in the low temperature radiating step. The follow-up studies where we also showed high temperature radiating steps. I showed that these time result task experiments are also very helpful to get information on rates of structural change. This could be changes in oxidation states of your redox couples. This could also be changes in your nickel coordination. And here we show by comparing the rates of change in the redox states that the vanadium 5 plus 4 plus redox couple is involved in the process of oxidative dehydrogenation ethanol. And the last example is an experiment when you combine typical kinetic experiments with these transient experiments to get an insight about the mechanism of the heavy spark catalysis as well as the deactivation mechanism. This is a slide showing the beam line where the data were collected. Switch slide source. Thanks a lot for your attention. Any questions for our speaker? The beam 3 shows up with the same activation. Is that a deactivation point? Or negative? Sorry, in the third example. We're going 4 by matching the catalysis. See the no, it's not a deactivation. It's just in the absence of oxygen, if you wait long enough, it goes 3 plus. As soon as we start with this reaction, right? So the reduction step is quite slow, the oxidation step is very fast. So as soon as you switch back on oxygen, you go back. Any other questions? Okay, let's thank our speaker.